5 organizers. Okay, so hi, my name is Adam Smith. I'm happy to be here. I'll be talking about differentially private algorithms for analyzing network structure, and specifically under a strong guarantee called node level differential privacy. Okay, so of course, graph data sets come up everywhere, and especially in the context of sensitive privacy, we're often looking at data sets where nodes correspond to people and edges correspond to relationships between people. And these things are, of course, potentially very sensitive. They can capture, might represent social or romantic relationships. They might represent friendships in an online social network, maybe financial transactions, phone calls, all sorts of things, doctor-patient relationships. So lots of different kinds of graphs where the nodes are people, edges are connections between people, and we want to analyze these networks and learn things about them without revealing too much about individuals. Okay. So this is really the central question that drove this line of research. What information can we release about these types of networks, subject to strong guarantees of privacy? And I won't go through it here, but there are lots of examples of de-anonymization attack, sort of failures of naive attempts to do this, right? You can sort of try to anonymize networks in various ways, and by and large, they don't work very well against attackers who have even modest side information about the network. So we'll be looking at algorithms for which we can make provable statements, and of course, given my own interests, I focused on differential privacy. Broadly, we'll say two data sets are neighbors if they differ in one individual's data, and an algorithm is differentially private if its output is roughly the same, if its distribution on outputs is roughly the same for all pairs of neighbors. Now, what it means that two data sets are neighbors is a subtle and interesting question when our data consists of some sort of network information. Okay, so there are at least two very natural variants. One is called edge differential privacy, where I'll say two graphs are neighbors if they differ in one edge. And then a differentially private algorithm would hide the presence or absence of a particular relationship in the network, okay, or the removal of a particular relationship from the network or its addition. Okay. A stronger notion that's harder to achieve, though, is called node differential privacy. So we'll say two graphs are neighbors in this notion if one can be obtained from the other by deleting a node and all of its adjacent edges, or alternatively by inserting a new node and an arbitrary set of new edges. So under either, differential privacy sort of mathematically makes sense under either of these notions. We'll say the algorithm is differentially private if for any two graphs that are neighboring under the relevant notion, the probability of any particular output is about the same under these two, under these two inputs. Okay, but really today I'm going to be focusing on. So there's lots of work on edge differential privacy, and some of it I've done. I'm not going to talk about that at all today, so I won't even try to survey it because there's a lot of it. There's less work on node differential privacy, and I'll talk more about that. And that's going to be the focus of today's of my talk. So, in order to sort of understand why node privacy is interesting and challenging, it helps to just play with a specific example. And somehow my animation got screwed up, but sorry. So one of the things that makes node privacy challenging is that under this notion of adjacency, lots of the things we want to compute have very high sensitivity. Okay, recall the global sensitivity of a function is the maximum difference you can see in that function when you consider two neighboring data sets. So in this case, graphs for whom where a person has been added to the network. And now we're going to look at, we're going to look at this notion of sensitivity, but under the addition of a node and an arbitrary set of edges to the network. So for example, we might look at a simple statistic might be the number of edges in the graph, or perhaps something a little more interesting, maybe the number of triangles in the graph, for example. And the problem is that these, if I look at a graph on n nodes, then the sensitivity of the number of edges in the graph is very high under this notion of adjacency, right? If I add one person to the graph with all possible edges, then I might have increased the number of edges in the graph by n or n minus 1, depending exactly on how you define things. And if I consider like number of triangles in the graph, then the sensitivity could be even larger. It could be as large as, well, sorry, everything's getting messed up. As large as n choose 2. Okay. And this problem we can't really solve this problem by considering, say, local sensitivity, because even under local sensitivity, most graphs, all graphs are neighbors of some other graph with a very different number of edges. So these are both global sensitivities, and they are also essentially local sensitivities. The first one is always the local sensitivity. The second one, it depends on the structure of the network, but it's generally high. So just looking at local sensitivity is somehow like not enough. We need to change our tool set further. Okay, and hopefully from now on the animations will be a little more rational. So there's sort of a broad, approach to doing this is to somehow restrict the class of graphs we consider, and somehow work with a restricted class of graphs. Right? So for example, let's consider, this is a very simple example, and we'll see more complex ones later in the talk. But what happens if I just restrict my attention to those graphs where the maximum degree is bounded above by some known quantity d? Okay. So it turns out that I can define a notion of global sensitivity for this subset of inputs. Okay, or sort of the sensitivity restricted to this subset of inputs. And a nice observation is that for lots of useful functions, this restricted sensitivity, the Lipschitz constant of f, when you restrict your attention to this subclass of inputs, is in fact not so high. So for example, if I look at the number of edges, then the global sensitivity restricted to graphs of degree at most d is now d instead of n. For triangles, it would be d choose 2. And so if we somehow had, if we could somehow get a promise that our input lay in this kind of nice class of graphs, then we could design much more accurate differentially private algorithms by, for example, in this case, adding noise proportional to this restricted notion of sensitivity. Okay. Now, this observation doesn't solve our problem because, first of all, we don't know what our graph looks like without actually looking at it. And what we'd like is a privacy guarantee that holds for all possible inputs, not only the inputs we hope we have, but the ones we actually get, right? Nevertheless, this sort of approach is like a key component of almost all the work on node privacy. That in some sense you want to project onto some like nice family of graphs, not always this family. So in fact, it sort of leads to this general technique that was first developed and interestingly appeared in 3 concurrent papers in 2013 by Chen and Zhou, Blum, Blocky, Data and Sheffet, and Vishwanathan, Nisim, Sodnikov, and myself. So the sort of broad approach is you're going to identify some nice set of graphs, for example, those graphs with bounded degree. Hopefully this includes the graphs you think you care about, right? Then you design an algorithm that's differentially private on these nice inputs. And then somehow you fix or extend this algorithm so it is private on all possible inputs. And exactly how you do steps 2 and 3, well, all 3 of these steps varies from, to some extent, from paper to paper, although there's some common elements. Okay, so these three papers looked at applying this to subgraph counting statistics. How many edges, how many triangles, how many different patterns of a given type might you see. There was some subsequent work that looked at degree distributions, and then another pair of papers that I was involved in that looked at fitting sort of fairly complex network models, statistical models, to graphs, and that's what I'm going to talk about more today, mostly today. And I'll just mention there's this sort of separate aspect to a lot of these papers, which is how do you choose this nice set of graphs in a way that actually depends on the data you have, rather than just sort of going in with your eyes closed and hoping. There's, again, sort of like a few different ways you might do that. This will come up, I guess, implicitly in this talk of Liu and Talwar that we'll see, I think, on Thursday this week. Okay. So what I'd like to do for the sort of the bulk of the talk is to tell you a bit about how this sort of philosophy and this approach plays out in the context of a specific problem that is of fitting what are called stochastic block models to network data. Okay. And I will now change slides because my co-authors are Beamer people. Let's see if this works. All right. So in this pair of papers, we consider a specific family of network models that I'll define in a minute. And we give new algorithms and also lower bounds and impossibility results on how well we can estimate the parameters of these models under no differential privacy. Okay, and in many, we look at estimating stochastic block models. In many regimes, we give an optimal, we give an algorithm that matches the non-private, the optimal non-private algorithm. And we also give some lower bounds showing that when you can't match the non-private algorithm, that sometimes that cost of privacy is unfortunately necessary. And we also give some interesting sort of special case results for a very special case, a narrow case of what are called Erdos Reny graphs. So this is like the simplest generative stochastic network model where all edges appear independently with a given probability p, and you just want to estimate p. And we give roughly tightly the optimal estimation rate there using sort of some new tools that I'll try to explain. Okay. So briefly outlined for the rest of the talk, I told you a little bit about node level privacy and some of the challenges that come up. I'll try to explain what stochastic block models are and why we might care about them. And then I'll try to summarize what we know about these models, both sort of in terms of what we can achieve and what impossibility results we can provide. And as I said, I'll spend a bit of time on the case, the very special case, the sort of what's called the one block case, the Erdos Reny model, and tell you a little bit about that. And if I get time, I'll sort of tell you about some fairly general tool that came up in these works that I think is broadly applicable. Okay, so what's a stochastic block model? So it's a generative model for a graph. It's specified by a number n and another number k. So n is going to be the number of nodes in the graph, and k is going to be a number of types of nodes. So there are going to be k kinds of nodes in the graph. Okay, so we have and then one other matrix which specifies how likely it is that nodes of two given types are to be connected. That sentence didn't work, but I'll explain again. All right, so here's the process that comes with these. So I'm given n, I'm given k, and this matrix, this k by k symmetric matrix of probabilities. So in the beginning, each node chooses a type independently of all other nodes. And for simplicity, we'll imagine that the types are uniformly distributed. They don't have to be. It can be any distribution on types. And then every two nodes will independently decide to create or not create an edge with probability given by the relevant entry of this connection matrix. Okay. So for example, if I have 12 nodes, then they might each choose they'll choose their 4 colors, so here are the 4 colors. And now, with probability according to which they look up in this matrix, they create an edge between them. Okay. So this is sort of a simple but actually fairly expressive model of how networks might arise, where there's sort of some underlying characteristic for each vertex. And the chances that Kobe and I share an edge are dictated by these characteristics. For example, where we work, what we work, our area of science, personality types, whatever it is. And so this the complexity of the model is controlled by this parameter k, which is sort of how many different types of people you imagine there are in the world. And it makes sense even to choose k very, very large. It makes sense to let k go to infinity, but then how well you can estimate the resulting object, of course, will degrade the more degrees of freedom you allow to the model. Okay. In the special case that k equals 1, then everybody is of the same type, and then the probability that any two nodes are connected is the same and independent of all other nodes again. And so that's what's called the Erdos Reny model. That's a widely studied generative model. Most of you have probably seen it in one place or another. Okay, so here's this is our stochastic model. I'll use the shorthand GNB to describe a random graph selected according to that model. So B is the matrix of parameters. Sometimes we'll need sparsity and we'll impose sparsity. So the restriction, the row sparsity restriction is just a restriction that all the probabilities in this matrix lie between 0 and row. Okay, so one way to capture sparse models in this sparse networks in this type of model is to let rho go down as n goes to infinity, if you sort of think about it that way. So the larger n is, the smaller rho might be, and that allows you to sort of capture essentially arbitrary relationships between the size of the network and the number of the density of the network, the fraction of edges that are actually present. Okay, these stochastic block models are very widely studied, at least without privacy considerations. So there are sort of nice connections with community detection problems. In complexity, there are various planted bisection problems and planted clique problems that can be sort of encapsulated by these stochastic block models. They come up in statistical physics. If you've ever heard of Summaries' regularity lemma, there's a sense in which it is talking about how well arbitrary graphs can be approximated by these types of models. So there's lots of nice work on these models and how they relate to the rest of the mathematical universe. And just one note, since I mentioned the word graphons earlier, graphons are roughly what you get when you take this model and let k go to infinity, so you can have infinitely many types. Every node can be its own type. And then you get meaningful models by sort of restricting this connection probability matrix to be not too complicated, smooth or something. All right, but I'm just going to talk about finite k for today. Yeah, Jayda.
Should we think n to grow along with k?
Yeah, essentially what we're going to do is we're going to look at how I'm going to talk about convergence rates. So I'm going to imagine n's going to infinity, and k will also be allowed to grow with n, and I'm not going to constrain the relationship. All right, so what's the statistical problem we're going to consider? We've got given one graph from this model, we'd like to estimate the matrix of connection probabilities using an algorithm that is itself constrained to be differentially private in the strong sense of being node differentially private. So even just to formulate this problem forget privacy, to formulate what we mean by estimating B correctly is a little tricky. And that's because I don't know the types don't really have names, right? It's not that there are these K types, but if I'm given G, I don't know, even if I could identify which vertices are of the same type, I don't know if that's type 1 or type 3, like there's no kind of necessarily clear relationship, because it's not like I know B, that's what I'm trying to figure out. So what we'll do is we'll say this algorithm that's estimating is going to output some matrix of connection probabilities. It's going to hope that it's close to B. But because it doesn't know the labeling of the K different types, we'll allow it to find a matrix which is close under any labeling. So we'll define the error in estimation of B by the output of A to be the minimum over permutations of the K labels of the sort of the closeness of the permuted matrix to B. Okay, so we're going to mod out by all permutations of the label names. Or alternatively, just consider two matrices equivalent if they are if they differ only in a permutation of the rows and columns.
Adam?
Yeah.
You don't make an assumption here that B is positive, definite, or anything?
No, there's no assumption. And it's just symmetric. So positive definiteness doesn't have a
the
particular meaning here.
Elements or probabilities are not likely to be more than the off-diagonal.
Not necessarily, no. But both make sense. It makes sense sometimes to have people of the same time more likely to connect, but depending on the kind of edge, the relationship you're modeling, that may not make sense. So that's not baked into the model.
Here the norm is 2 norm, spectral norm, or?
Yeah, sorry. This is just, that's a good question because I didn't explain it. This is just like it's the Frobenius norm if you want. It's just that like I'm going to think of the matrix as a big list and look at the Euclidean distance between the two resulting vectors. And you could put any other metric, sort of reasonable metric here and derive similar results. But the exact form would change. Yeah, Yushang.
So the assignment of nodes to each block is not part of the output?
No, and that there are a few reasons for that. So first, differentially privately, you couldn't node differentially privately. You couldn't hope to do that because you'd be like naming people. But also there are even non-privately. There are lots of interesting settings where you've got enough information to estimate B well, but not to estimate which nodes are of which type well, which is sort of surprising. Turns out those are like not the same problem. Okay, so sorry. So we're going to look at just mean squared error, which is the expected, given a model B and an estimator A, the mean squared error is the expected delta 2 distance squared between the output of the algorithm and the true model. There's some worst case performance. We'll look at minimax bounds, so we'll look at the worst case over all B that are row sparse and K by K. That's going to be our metric of how well the algorithm does. And what we're really interested in is sort of what is the performance of the best algorithm. So that's the quantity we're trying to nail down. Notice that these two measures here, as I formulated them, they kind of assume that the true graph was generated from a model of the same type that you're trying to estimate. Right? There's a nice match between the kind of generative form of of nature and the model you're trying to use, which in general we don't expect. I'm going to stick with that for the talk, but in the paper we talk about a more general setting where we don't sort of constrain the model from which the graph was generated. Okay, so let me tell you what we do know about these models and also what we don't. So roughly speaking, what we show in sort of, there are a pair of papers with the first paper with Christian Borgs and Jennifer Chase from MSR, and the second paper with those two plus Ilyas Tzadik, who's a student at MIT, who will be going to NYU next year as a postdoc. And so what we show in the stronger of the two results, the second result, is the following bound on the estimation rate. Okay, so here it is. You can admire it. It's got a lot of terms, so let me sort of break it down at least a little bit so it's easier to think about. So let's get some intuition for what's going on. First of all, I think for all intents and purposes, you can ignore rho. And in retrospect, it sort of occurred to me as I was preparing the talk that I should just remove rho entirely from the talk. But then I was afraid that I would introduce like crazy inconsistencies. So I didn't. But just ignore rho, or pretend it's 1. We've got a few different terms here. These terms don't involve epsilon, and these ones do. The terms that don't involve epsilon, there are 2 of them, and they sort of naturally come up. There's a term that's k squared over n squared, and that is, it turns out like the mean squared error you would get if I told you all the types of the vertices, and you just had to figure out, with no privacy constraints, what the parameters of the matrix are, how well, try and get as accurate an estimate as you could of each of the entries of this connection matrix. That's the term you would get. On the other hand, if I told you B, and I asked you to try to figure out where the vertices lie, then roughly speaking, you would get this second term. That's like not as clear how that comes up, but one sort of not entirely honest explanation is to say that there are sort of k to the n ways of assigning types to vertices, and you get some dependence on the log of that many types. So that's like how much information you need just to figure out what that assignment is. As I said, that's not really an honest explanation of what's going on, but we'll take it. Okay, so that's where these terms come from, and then we'll talk more about these terms in a minute. We developed an algorithm that's not efficient in this original paper, and then the analysis I'm presenting here came later. Okay, so one thing we can say is that the left-hand terms, they have to be there, because that is actually the optimal non-private rate. So that was worked out over a number of papers, but the full statement, and some papers that, including a paper that Audrey and I wrote together, but the full statement came in this paper of Klopp, Tzibakov, and Verselen. And they showed that this is the tight upper and lower bound for estimating things with no privacy constraints. So our bound is sort of that plus some other stuff, which is the form you'd expect. And in a number of regimes, this first term dominates the second term, and so then you get sort of privacy, for free, at least asymptotically. You get the estimation error dominates the distortion you introduce for privacy. Oops. Okay. So I'll explain more about where these other terms come from as we go, but they are basically coming from different parts of the algorithm itself.
I don't know, sorry, can you remind me what rho is?
Sorry, rho is 1.
No, but but you just said that the second term is smaller than the first term, and so that's only true when rho is not.
Yeah, so rho is a density parameter. So it tells you roughly the expected density in the graph, and it's in this context technically it's an upper bound on the connection probabilities. So yeah, for things to match up nicely, you need rho to not be 1 to go to 0. Okay, so the basic idea of the upper bound, the algorithm, is reasonably natural. So the first thing we do is to measure, get a rough idea of how many edges there are in the graph. So it turns out this is not super easy to do, but we don't need a very good idea of how many edges there are in the graph, and so we just use the Laplace mechanism calibrated the global sensitivity of the number of edges. It turns out that's good enough for our purposes. It introduces mean squared error about 1 over epsilon squared n squared. It's actually without the square it would be 1 over epsilon n. And then given that sort of that estimate of the parameters that allows us to constrain things, we run. It's an inefficient algorithm, unfortunately, and it's an open question to come up with a more efficient version, even non-privately. But what we're going to do is sort of use the exponential mechanism in a nutshell to try and select the model that fits the data as best as possible, but using this density estimate to constrain the sensitivity of the scores that come up in the exponential mechanism. Okay. To a first approximation, what we'll do is we'll take the score of a given model b hat in the exponential mechanism to be the delta 2, actually there should be a square here, the squared error of b hat in estimating the graph G. And I realize I don't have the explanation on the slide of what that means, so let me explain that. So we're looking at the difference between this little k by k matrix, which is a given candidate model, and a big graph represented by its adjacency matrix. So that's, got lots of rows and columns. So what does it mean to look at the distance between these? Well, what we're going to do is just take the minimum over maps from n to k of a sort of blown up version of b hat. Okay, so we're going to take the minimum over assignments of types to edges of the Frobenius distance between the blown up version of b hat. And what I mean by that is we'll take like a big, it's now a big matrix, so G is unchanged. But then the way you find the entries of this blown up version of b hat is that you'll use pi to tell you, for I and j, you're going to look at b sub pi of I, pi of j. Okay. So you're looking at the sort of best assignment of types for this graph of using the proposed edge connection probabilities in b hat. And and then you square that, which is not, I'm not going to write it on the board, but that there should be squared. And it turns out even that's not exactly the score we use. We have to make some other changes to it. Yeah.
Be the value of probability, then so what is the...
What does it mean?
Yes.
Well, so they're probabilities, but they're numbers between 0 and 1. The entries of the adjacency matrix are also numbers between 0 and 1. And so we're just going to look at the Frobenius distance between. So it's not going to be very low. It's going to be pretty big, right?
Yes,
But that's okay. I just need it to be better for the right model than it is for the wrong models, right? And actually, there's some additional stuff we have to do. We have to modify this thing to make it lower sensitivity. One of the modifications is sort of relatively easy to explain. We'll use the density estimate from the first step to constrain the global sensitivity of the score functions using sort of what's called a Lipschitz extension. It's just some extension of the function from those graphs with the right density to all possible graphs. And then there's some other stuff that's maybe not so interesting, just some rewriting of this expression, and you can throw out some high sensitivity terms that don't matter. All right, so so this is the structure of the algorithm, and what makes the problem challenging is that analyzing how this exhaustive search algorithm works with noisy scores is non-trivial. Well, analyzing how it works with perfect scores, which is what KTV did, is not so easy. And modifying that analysis to take into account the extra noise is also not so easy. And in fact, we tried, the first time, Jennifer, Christian, and I tried once and didn't do it very well. And then Ilyas came along and came up with a really nice argument that improved the analysis. Yeah, there's a question. No, it's good. All right.
Another question?
Yeah.
So do you discretize the probabilities or?
We do. It's not clear you have to, but it's easier.
If you use the exponential mechanism, you have to.
Maybe, right. At least to run it in a finite amount of time. Yeah. Details. Okay, so I'm not going to go through the net analysis the net argument that makes this work, because I didn't know how to do it nicely in a sort of shorter talk. But I'll tell you a little bit about optimality and some of the things that come up, and because they're a little easier to understand, and I think maybe more insightful. Yeah.
I guess I'm sort of blacking out on the intuition. Why do you need the Lipschitz extension to the score?
Yeah. So that.
What would be the worst case change that a node could cause that would be so devastating to the score?
Well, so this actually mostly comes up when you're in the sort of lower density cases, and there you can basically if the adjacency matrix is relatively sparse, then adding one vertex that's connected to everybody will just screw everything up.
But in those, I mean, what do you consider sparse? Because usually that noise, you had in the very first one, introduces linear, right? You're counting the number of edges up to linear error. So what do you call sparse? Like linear number of edges, or again?
So it turns yeah. So the good question. So think of it as at least a logarithmic average degree. And to get good results, you need it a little higher than that. At least for large, it depends on k. So there's sort of this relationship between k and n and rho in both sides that is not so sort of crisp to explain. So I'll be honest, I didn't sort of focus on the case of very low rho. In the paper, we try to work everything out as clearly as we can, but for the talk, I'm sort of not really pushing the rho as low as it can go. Okay, so the question that I'll spend the remaining time I have on, which is not that much, is what can we say about these other terms? So one thing we can say is that this term is really necessary. Okay, so we argue that you can't really get away without this type of dependency on n and epsilon, and this term basically comes from that initial step where we estimate the density. And I have an argument on the slides that I'll mostly skip. It's just there's some relatively simple family of two-block models where you can argue you really need this term. Okay. Just to estimate the number of nodes, roughly speaking, the number of nodes of each type. We don't know if this term is necessary. This term comes out of the exponential mechanism, and in fact, I would imagine that using under epsilon delta differential privacy, you can get rid of the square. I suspect that is the right that's optimal, but I don't know proof of that. So I'm going to just skip over the lower bound for k equals 2 because it's a reduction to binomial estimation. It's fairly simple. And talk about the case of k equals 1, because I think it's an interesting sort of weirdness. That, let me explain. So what we argue is that in the case when k equals 2, we need this term to be there. The 1 over n squared is necessary. And one might conjecture that that's even necessary for k equals 1, just to estimate the density of the graph of a Erdos Reny graph. But surprisingly, the answer is it's not necessary. If k equals 1, we can actually get like a big improvement in the estimation rate. And I'll spend what time I have left explaining that. So here's a very simple open problem. Given a sample from a graph G and P, so let's say n is known but P is not, we want to estimate P. Okay, it's a simple problem. Non-privately, the thing to do is you look at the number of edges in the graph, you divide by n, choose 2, that's your estimate, it's as good as it gets. Right? Under edge differential privacy, also it's a binomial estimation problem. You've just, like, all edges are equally likely to be there or not. Very simple. Under node differential privacy, it's more subtle because the privacy constraint means that I can't just treat this as n choose 2 independent samples from a binomial, because they're kind of tied together by the fact that they're attached to specific vertices. So the task for k equals 1 is to come up with the estimation rate for the Erdos Reny model. Okay, so the natural thing to do is what I mentioned earlier, just to add Laplace noise, calibrate it to either the global sensitivity or maybe some degree constrained version of it. If you know the degree in your network is not so big, maybe you can do a little better using the techniques from these previous papers that I mentioned. It turns out even that's not good enough. And I won't go into why the second statement, but I'll explain why just the basic thing doesn't work. Or doesn't work as well. So the basic Laplace mechanism will give you this rate, 1 over n squared. That's the basic estimation rate non-privately, just the fact that you have n choose 2 samples, n choose 2 edges to get information from. And then this extra term is the noise. It comes from the noise you add using the Laplace mechanism. And so and this 1 over n squared you can't avoid. So really the question is what term goes there? What's the epsilon dependent part? So let me see if I can. I'll skip over the explanation of what the Laplace mechanism does. But I'll just explain try to explain where it does something weird. So the Laplace mechanism, we calibrate the noise to the global sensitivity. The global sensitivity is obtained by considering 2 graphs that differ in one vertex that goes from having no edges at all, or almost no edges at all, to lots and lots of edges. Okay? So maybe I add a vertex that's connected to everyone. Okay, so that's how I get the global sensitivity and the local sensitivity, as we mentioned earlier. But actually, sort of what we realize playing with it is that when you're dealing with a graph that's sampled according to G and P, you don't actually expect to ever see a vertex with very high degree, nor do you ever expect to see a vertex with very low degree. In fact, you expect all the vertices to have almost the same degree. And so what we know is that if we were considering 2 vertices, two graphs that differ in the connections of this one vertex v, then even if those edges get rewired completely, if the total number of edges changes drastically, then I kind of know I'm not dealing with a graph from the right model, and so I can sort of ignore the other graph, the weird-looking graph. Okay, so if I get a big change, then either G or G prime is going to be sort of atypical for my model. So instead, what we'll do is restrict our attention to those graphs that are typical, and the sort of superficial notion of typicality is going to be that all the degrees have to be where they're expected to be, and then we'll see that it turns out that's not quite enough, and I'll explain it in a second why that is. But that's going to be the basic idea. So the idea is we want to get an algorithm that works for typical graphs, but is private for all pairs of graphs. Okay. So the idea is we're going to construct a good typical set. And good means that it should arise with high probability under this model. So for any p, the probability that G lies in my typical set should be high, or the probability that it falls outside of it should be low. And somehow the sensitivity should be small, meaning the global sensitivity should be small. So for all pairs G and G prime, the change between the number of edges in G and the number of edges in G prime should be about this quantity, square root of log n you can ignore, 1 over n to the 3/2, times the number of vertices that were rewired to get from G to G prime. And that's going to be like the sorry, square root of n, well, yeah, we're dividing by n squared. So square root of n times the number of vertices that were rewired. And that's going to be the key step. And the family of graphs we use, it turns out it's not enough to constrain degrees in the graph, but it is enough to constrain cut densities. So the family of graphs we look at is that we say a graph is typical if for all cuts S, so here S is a set of vertices, and for the actual estimated density of the graph, the actual edge density of the graph, the number of edges crossing, so I'm going to consider some cut. I'm going to look at the number of edges that cross the cut and also at the number of edges inside the cut. And those two should be close to what they would be in expectation under the model with these parameters. So they should be roughly p hat times sort of the number of edges leaving the cut plus the number of edges inside the cut. And it turns out that with some messing around, sorry, this t should be the size of S. That should be plus or minus the size of S. And so it turns out that I mean, it's a sort of standard probabilistic result that Erdos Reny graphs satisfy this type of constraint. And if they satisfy this type of constraint for all cuts or all sufficiently large cuts, and for all cuts up to a certain size at least, then we get a global sensitivity constraint of the form we need to, say, use something like the Laplace mechanism. And so this is really where the work goes into, is arguing that this constraint is sort of sufficient to make things work. Okay. So that's sort of the first part. We need that the algorithm behave well on this restricted class of graphs. And then we also need to be able to take this algorithm and kind of lift it up to work on all possible graphs. And for that, turns out the sort of extension results that were in previous work don't quite fit. And we need to do we need something a little more general. And I'm not going to even explain why we need the generality, but believe me. And essentially what we need is a way to say, if I can take any algorithm that's differentially private when restricted to H, I can create a new algorithm that's differentially private on all possible graphs and behaves identically to my original algorithm on H. Okay, and so that's the general extension lemma that we show that I won't have time to prove to you, but that's the basic idea of that lemma. Okay, so in this context, it gives us a result, and it gives us this estimation result, and also we have some evidence that this result can't be improved any further, although it only works for constant epsilon, so it's not really a full proof. I should mention that Adam Seelfon and John Ullman in recent work have come up with a polynomial time version of this algorithm. Okay, so I went through sort of what we know about this model and a little bit about the techniques we can use and the fact that for certain special cases we get really different behavior. And so I think it's an interesting class of models to play with. We also have this sort of more general extension lemma that I'll just state very quickly. If I've got any algorithm, sorry, you can ignore all the other text, just focus on the blue box. Let's say I've got an algorithm that's epsilon differentially private on some subset of the input space. This doesn't have to be no differential privacy, just any privacy with respect to any adjacency notion. Then there exists an algorithm defined on the entire input space, which is also differentially private. The parameter gets blown up by a factor of at most 2. And it behaves identically to the original algorithm when restricted to H. This extension, this new algorithm may not be computable efficiently, but it exists. And it sort of it gives us a very easy way to at least demonstrate the existence of certain types of algorithms, even though maybe putting our hands on efficient versions remains non-trivial, and that's what some of these papers that I mentioned earlier actually do in special cases. Okay, so I'll just wrap up with some quickly with some open problems. There was this sort of term that came out of the analysis of the exponential mechanism. We don't know if it's necessary. And in fact, I suspect you can at least improve it somewhat using epsilon delta differential privacy. But it would require a different algorithm. I don't think it'll follow directly from the exponential mechanism. There is the mention, as I mentioned, we have this lower bound, this upper bound for the Erdos Reny model that's partly matched by a lower bound, but effectively it only works for small values, for larger-ish values of epsilon, meaning constant epsilon. So getting a lower bound that works for all epsilon as epsilon goes to 0 remains open. Oops. Time efficiency is sort of a big block here. It's true in the for the non-private analog of these problems, our understanding of what's possible in polynomial time is not complete. But for the private analog, we know like nothing. So it is still less than what we know in the non-private setting. And then there's this sort of hunch that we have that this extension lemma can be used to give statistically useful algorithms in a range of other settings where you sort of first design an algorithm that works on inputs that are typical for the model and then just wave your hands and say, okay, that means I can extend it to all possible inputs. And so it allows you to just only worry about the typical ones. More generally, for the class of no differentially private algorithms, there are lots of things that remain open. So as I mentioned before, there's sort of this question of efficient algorithms for block models. Can we even match what's known non-privately? Not that I know of. Continual release of interesting statistics in the no differentially private setting is non-trivial. So there's a model called the continual release model where you've got data coming in over time and you want to maintain a data structure that allows you to answer queries about the current data set. So there's a sort of relatively recent paper of Song et al. That looks at this, but they do this sort of assuming a niceness condition on the graph, not enforcing it. Okay, so that their algorithm is not private when the niceness condition is not satisfied. And so in some sense, the hard question there that remains is whether or not you can get these types of extension results, but in this continual release setting. There's inference on other natural graph models. There are lots of them. Questions about how do we analyze graphs with attributes. So for example, we might want to regress income of a given person on that average income of their neighbors or things like that. Any model like that is sort of under node privacy type guarantees is hard to work with, and we don't really have good tools for. And simultaneous release of many different statistics is also non-trivial. Yeah. Okay, so I'll just stop there. Thank you very much.
There isn't much time as the next speaker sets up, but a few questions, and I suspect many of